So in previous discussion, we have discussed what are reference electrodes, and we have taken an example of calm electrode and discussed the construction and working of calm electrode, isn't it? So today we are going to discuss a different category of electrodes, ion selective electrodes, and take an example of ion selective electrode, that is glass electrode, and discuss what are glass electrodes. So let us see what is ion selective electrodes. As the name indicates, ion selective means this is specifically designed for a specific ion. So ion selective electrodes are type of reference electrode which the or the ion selective electrodes are type of reference electrodes where the electrode potential of these electrodes responds or depends upon concentration of only specific type of ions when dipped in a solution containing mixture of ions. So ion selective electrodes responds to concentration of only a specific type of ions when dipped in a solution containing mixture of ions. So for example, just 115 years back, if you want to test your water sample, you used to book 3 months back, right? If you get a water today from your borewell, if you want to know whether the water is potable or not, you're supposed to send the sample to the laboratory. By the time you get a reply, it used to be almost 3 months. But now that is not the case. So immediately you can take the pen out of your you got portable devices. So as soon as you dip the device in the water, it gives the TDS, it gives the pH, it gives the fluoride. Why? Because the entire credit goes to your ion selective electrode. For instance, if you want to know the fluoride concentration present in the water sample, so what do is you take the electrode designed only for fluoride, you dip in the water sample. So this water sample may contain calcium ions, or it may contain lithium ions, or it may or it may contain fluoride, or it may contain chloride. So but you want only fluoride, so going to dip electrode which is sensitive only for fluoride. So this electrode gives a reading only for fluoride ion concentration. If there is fluoride ion, it gives it. If there is no fluoride ion, it will not give. So if it is more or less, it depends upon this. If there is no fluoride at all, then it will not give. So if you want to determine the calcium ion, then you have a separate electrode. If you want to determine the concentration of magnesium ion, you have a separate electrode. So these are called as ion selective electrodes. So there are different types of membranes. These are solid state membrane, liquid membrane, heterogeneous membrane, and glass membrane for ion selective electrodes. So today we are going to discuss the construction and working of glass electrode. So glass electrode. So glass electrode is an example for ion selective electrode. So glass electrode is made up of a special type of glass membrane. This whatever bulb you have, right, is made up of a special type of glass with low melting point and high conductivity. Why the conductivity should be high, I'll tell you. Okay, so the high conductivity and low melting point. So the bulb contains a internal reference solution. This is usually used as 0.1 molar HCl, and it also contains an internal reference electrode, that is silver chloride electrode. Okay. The entire setup is dipped in a solution containing H plus ions of unknown concentration. When this is dipped in a solution containing of unknown concentration, so let us assume it is dipped in a solution containing H plus of unknown concentration. When it is dipped, what happens? So due to difference in concentration of H plus ion exchange reaction occur. So ion exchange reaction occur across the membrane. So due to this, what will happen? This ion exchange reaction occurs until the concentration of H plus ion inside the bulb and outside the bulb are equal. Once the concentration of the H plus ion inside the bulb and outside the bulb are equal, so no more H plus ion exchange reaction will occur. So the main reason for what is this ion exchange reaction to occur is due to difference in concentration of H plus ion. So due to this ion exchange reaction occurring at the bulb, a potential is developed across the boundary and that potential is called as boundary potential. Okay, so let us see what is the reaction that occurs. So the reaction that occurs across the bulb is H plus Na plus Gl minus gives Na plus and H plus Gl minus. So the H plus present inside the bulb will get exchanged for the H plus present in the outside the bulb. So this reaction occurs until the concentrations of H plus ions inside the bulb and outside the bulb are equal. Okay, so let us see what are the how this cell can be represented. So glass electrode is represented by this Ag/AgCl, this internal reference electrode dipped in 0.1 molar HCl and the glass membrane. The electropotential of glass electrode is determined by Eg equals Eg naught minus 0.0591 pH. The electropotential of glass electrode is given by Eg equals Eg naught minus 0.0591 pH, where Eg naught is a constant. So let us see what is Eg naught. So Eg naught is given by, so Eg naught is equal to, it is sum of electrode, that is internal reference electropotential EAgAgCl and asymmetric potential E asymmetry and a constant K. Okay, so E naught G is electropotential sum of internal reference electrode, asymmetric potential and K. So inside the glass electrode you have this, so you are going to consider this. So what is this asymmetric potential? So asymmetric potential is nothing but, I'll tell you. So ion exchange reaction occurs inside the, this ion exchange reaction occurs until the concentration of H plus ions inside the bulb and outside the bulb are equal. Once these both are equal, the boundary potential should be zero, right? So, but in practical, even when the H plus ions inside the bulb and outside the bulb are equal, the boundary potential was not found to be zero, and that potential is called as asymmetric potential. We're going to consider even that asymmetric potential also. Okay, so E naught G is constant. We're going, that is sum of internal reference electropotential, asymmetric potential and constant K. So this constant going to substitute here, measure the pH of the solution, substitute, it gives you the electropotential of the glass electrode. Okay, so now let us see what are the advantages and disadvantages of the glass electrode. So this glass electrode can be used when in the presence of oxidizing and reducing agents and also complexing agents, but it cannot be used if it is pH of the solution is more than 12. So it cannot be used in the presence of dehydrating agents such as acids and also in presence of alcohols, because the membrane is very sensitive. Okay, so we have this glass electrode is used in pH measurements of all. It might be water, it might be liquid, it might be blood or urine. So measurements of anything it is used. So in order to analyze the food, cosmetics are going to apply it to the space, right? Because cosmetic, environment regulations, solid, acidity of the solid decides what type of crop you are supposed to grow. So that also are going to measure in order to determine the acidity of the solid, you're going to use the glass electrode. So there is a small video here which shows the ion exchange reaction which occurs, which I showed you there. So how it occurs and how sensitive the glass membrane, you can see over here in this reaction.
Many liquids are essential in our daily life. They may include water, beverages, dairy products, chemicals, acids and bases, or pharmaceutical products. The quality of these liquids is determined by their chemical properties. To assess these properties, various principles of measurement are used. One of these principles is pH measurement according to the potentiometric principle. The principle can be traced back to 1909, when the Danish chemist Søren Sørensen introduced the so-called hydrogen ion exponent pH+, to describe the concentration of hydrogen ions in a solution. This was the basis for the development of the conventional pH scale. In 1889, Walter Nernst formulated the Nernst equation that for the first time related electrical voltage to ion concentration. The Nernst equation derived for pH is the physical basis for pH measurement according to the potentiometric principle. Potentiometric pH measurement is the measurement of a potential difference using so-called glass electrodes or non-glass electrodes. In the case of glass electrodes, the pH-sensitive element is a glass bulb that is fused to the end of a glass tube. The electrode is filled with a neutral potassium chloride solution buffered at pH 7, and contains a silver-silver chloride wire that forms the electrical
internal
connection.
reference electrode.
The reference system is located in the outer glass tube and also consists of a silver-silver chloride wire in a potassium chloride solution. A so-called junction protects the reference system from the medium to be measured without disconnecting the electrical connection between them. The pH value is calculated from the potential difference between the reference system and the measuring system. Let's take a closer look at the pH-sensitive glass bulb to understand how this potential difference is formed. Diluted hydrochloric acid, for example, contains large negatively charged chloride ions and small positively charged hydrogen ions. When the pH sensor is immersed into this acid, the hydrogen ions are able to penetrate the boundary area of the glass membrane, the so-called gel layer. The considerably larger chloride ions remain in the solution. The result is a charge separation. The same process occurs on the inside of the sensor with the neutral solution buffered at pH 7 that has a constant concentration of hydrogen ions. If the hydrogen ion concentration, hence the pH value, on the inside differs from the concentration on the outside, a measurable potential difference forms. If the hydrogen ion concentration on the inside is lower than on the outside, as shown here, the measured solution is acidic with a pH value lower than 7. If the hydrogen ion concentration is identical on both sides, no potential difference forms and the measured solution is neutral with a pH value 7. The measured solution is basic if the hydrogen ion concentration inside the glass bulb is higher than in the measured solution. pH measurement with non-glass sensors is based on so-called ion-selective field effect transistors, short ISFET. They use a MOS transistor arrangement, which contains a pH-sensitive layer instead of a metal gate. Positive hydrogen ions forming at this layer cause the charge to be separated on the other side. As a result, the area between source and drain becomes conductive. The resulting flow of current is in direct proportion to the pH value of the medium. Just like the glass sensors, the ISFET sensor also needs a stable reference potential. The potential that forms at the ISFET can then accurately be measured against it. The reference system is also protected from the measured solution by a so-called junction. The potentiometric measuring principle by Anderson-Hauser enables highly accurate pH measurement for better product yields and less waste. We offer a solution for all applications, even in those industries that do not tolerate glass. For further information on liquid...
So you came to know how it is, how it works, isn't it? You can see. So that solution, whichever is inside the glass bulb, it will be taken as internal reference electrode, internal reference solution. Depending upon that, the pH can be calculated. The potential difference will be calculated. Based on that, the electrode tells you that is pH is, solution is acidic, basic or neutral. If it is less, then it is acid. If it is equal, it is neutral. If it is more, it is alkaline. Okay. Thank you. In the next discussion, let us see how to determine the pH of a solution using glass electrode. Okay. Thank you.